Hey everyone, in this video we're going to continue our work with geometric sequences. The first example, if the first term of a geometric sequence is 4 and the second term is 2, determine an explicit formula to find the nth term in the sequence. So just as a reminder, the explicit formula for a geometric sequence is a sub n equals a sub 1 times r to the n minus 1. Right, the explicit formula is an exponential function. The coefficient is the first term, the base is the common ratio, and because the coefficient is the first term, we have to move the exponential function 1 to the right. Okay, so now let's take the information they've given us and write it out with our subscript notation. So first term is 4, so a sub 1 equals 4, and the second term is 2, so a sub 2 equals 2. So they happen to give us 2 consecutive terms of the sequence, which is really helpful. This sequence would be 4, 2, and then continue on. I don't know what the values would be, but I know it's geometric. So if I figure out how to go from one term to the next, and it's geometric, so I have to figure out what I'm multiplying or dividing by. So in this case, I see it as multiplication by 1/2. So the common ratio is 1/2. Another way to think of this, and why it's called the common ratio, is we can take the ratio of 2 consecutive terms. Meaning, I have the second, I have the first. So the ratio would be a term divided by the term before it. So I can do 2 divided by the term before it, which would be 4, which does give me that ratio of 1/2. So if you ever have a geometric sequence that you're having trouble figuring out what the common ratio is, then actually find the ratio. Take a term, divide it by the term that comes before it, and do that for a few consecutive terms and see that you get the same ratio out each time. So now we have the common ratio, we have the first term of the geometric sequence, so our formula is a sub n equals 4 times 1/2 to the n minus 1. And we can use that to find any term of this geometric sequence. Next, given 2 terms of a geometric sequence, determine an explicit formula to find the nth term in the sequence. Assume n is greater than or equal to 1. So we're just assuming that we're starting the sequence with a first term. A sub 1 equals 3 is that first term. So they've given us 2 terms, they just don't happen to be consecutive terms. So we can't take the same approach we did in the previous example. Okay, so we do have the first term, so that is helpful. So let's write out the formula with what we know. So a sub n equals 3 times, we don't know the common ratio, to the n minus 1. Okay, so really the only thing we're missing is the common ratio. If we had the second term, that would be really easy. We just happen to have the fourth term. But what we can do is we can use this and the formula that we've written so far to solve for the common ratio. So if we know the fourth term, we can plug n equals 4 in. So a sub 4 equals 3 times r to the 4 minus 1. A sub 4 is 375 equals 3 times r to the third. Now we want to isolate r cubed, so it means we have to divide both sides by 3. So we have 125 equals r cubed. Now to solve for r, we're going to take the cube root of both sides of our equation. No issues when we're taking a cube root, so that's 5 equals r. Right? 5 times 5 times 5 is 125, so the cube root of 125 is 5. So we solve for the common ratio that we were missing here. So now we can put that back in. A sub n equals 3 times 5 to the n minus 1. And there we have our formula. Perfect. Next, same directions, but they've given us a sub 3 equals negative 16 and a sub 5 equals negative 256. So they don't give us the first term. Well, how are we going to take the same approach from the previous example and apply it here? Well, it comes down to understanding that the geometric formula is just a translation of an exponential function. Okay, so if I have the third term, I can write the explicit formula with the third term. I'll use negative 16 as the coefficient. We don't know what the common ratio is. Now, instead of moving 1 to the right, because the coefficient was the first term, since the coefficient is the third term, we're going to move 3 to the right. So again, we're tying back in with that idea of transformations. We're taking that exponential function and we're shifting it 3 to the right so that it matches up with this particular sequence. Okay, so now that we've established this, which is really helpful, we can use the other value they've given us, the fact that a sub 5 is negative 256, to solve for r. So we can plug in 5 for n, so a sub 5 equals negative 16 times r to the 5 minus 3. A sub 5 is negative 256 equals negative 16 times r squared. We need to isolate r squared, so we'll do that by dividing negative 16 on both sides of our equation. So 16 equals r squared. Now we're going to take the square root of both sides. Now when we do that, remember what happens. It becomes an absolute value equation. 4 equals the absolute value of r, which means either r equals 4 or r equals negative 4. Well, what does that mean? That means that we have two possible formulas here, not just one. We can either have a sub n equals negative 16 times positive 4 to the n minus 3, or we can have a sub n equals negative 16 times negative 4 to the n minus 3. We need to include both because they're both potential formulas given those two terms. Now, why does it make sense that there's two? Well, a sub 3 and a sub 5 are two terms away, right? 3, 4, 5. Well, if I multiply by positive 4, it would be negative 16, then negative 64, and then negative 256 still. If we multiply by negative 4, it would be negative 16, then positive 64, and then negative 256. So two different sequences still have the same two terms that we were given. Hence, we have two formulas, one for each sequence. Okay, so two different things to focus on in this example. First, writing the formula when we don't have the first term, right? Shifting it so that we can use whatever term we have as the coefficient, right? So if I wanted to, I could have used the fifth term, negative 256 as the coefficient, then it would have just been n minus 5. And then also this reminder that when we take the square root of r squared or x squared, it becomes an absolute value equation that we're solving. Find the eighth term of a sequence with a first term of 243 and a common ratio of 1/3. So now we're actually going to use our formula to find another term in the sequence. So first term of 243, so a sub 1 equals 243. Common ratio is 1/3. So our formula is a sub n equals 243 times 1/3 to the n minus 1. Shift everything 1 to the right so that this is the first term. And then we're going to use this to find the eighth term, so that's n equals 8. So a sub 8 equals 243 times 1/3 to the 8 minus 1. So we have a sub 8 equals 243 times 1/3 to the 7th. Now let's use the calculator to find this answer. Okay, so we have 243 times 1/3, so we'll do 1 divided by 3 in parentheses for the 1/3. Remember the exponent key is the up arrow, to the 7th, and hit enter. Now that gives us a repeating decimal. Be much nicer if it was a fraction, So we can hit the math key, and the first choice is arrow frac, which means it's going to turn a decimal into a fraction if it can. So we hit that, and hit enter, and it becomes 1/9. So the 8th term of this sequence is 1/9. Now, could we have just multiplied by 1/3 over and over and over again? Yeah. 8th term, okay, that wouldn't be too bad. What if I gave you the 21st term, the 100th term? You'd be at it for a while. So this is the best way to answer that question, and oftentimes they're going to tell you to do this algebraically, which means you have to create this formula. Find the 10th term of the sequence -2, -6, -18, -54, -162, continuing on. So first thing we need is the common ratio. So to go from -2 to -6, that's times 3. -6 to -18, that's times 3. -18 times 3 is -54. And then -54 times 3 is -162. So our first term is -2. Our common ratio is 3. So the formula a sub n equals -2 times 3 to the n-1. Again, really helpful when we do have the first term. And now we want to find the 10th term, so that's when n equals 10. So a sub 10 equals -2 times 3 to the 10-1. So we'll do that subtraction in the exponent first. So a sub 10 is -2 times 3 to the 9th. Again, we'll use our calculator here. So we'll clear that out. So we have -2 times, in parentheses, 3 to the 9th. And we hit enter. -39,366. -39,366. That's the 10th term of our sequence. Perfect. Find the 11th term of a geometric sequence with a third term of 0.5 and a 6th term of 4. Okay, so first thing with our sequence notation, a sub 3 is 0.5, a sub 6 is 4. We're looking for the 11th term. Okay, so they don't give us consecutive terms here, which would make it easier for us to find the common ratio. So we have to use a strategy that we used previously. So first let's write the formula using the third term. So that's a sub n equals 0.5 times the common ratio, which we don't know, to the n-3. Shifting right 3 so that this coefficient is the third term. Now we're going to use the 6th term they gave us to find the common ratio. So a sub 6 equals 0.5 times r to the 6 minus 3. So a sub 6 is 4, so 4 equals 0.5 times r to the third. We need to isolate the r cubed, so divide by 0.5 on both sides. So 4 divided by 0.5, that's 8, equals r cubed. Take the cube root of both sides, and we get 2 equals r. Okay, so a sub n equals 0.5, 2 to the n-3. And that's correct, but it doesn't matter because we're not done. We need to find the 11th term. So when n equals 11, we have a sub 11 equals 0.5 times 2 to the 11 minus 3. So a sub 11 is 0.5 times 2 to the 8th. Now, just to work through this without a calculator, we could easily plug this in. 0.5 is 1/2, and then times 2 to the 8th, that would be 2 to the 8th over 2. Now remember our properties of exponents here, that's 2 to the 1st. Subtract those exponents, that's 2 to the 7th. So a sub 11, 2 to the 7th is 128. So the 11th term of this sequence is 128. We had to work a little bit harder to get that compared to our other examples because we first had to solve for the common ratio and then set up the explicit formula and plug in 11. Write an explicit formula to find the nth term in the following geometric sequence. Assume n is greater than or equal to 1. So looking at that sequence, there are a lot of letters there, but it doesn't change our approach. To write the explicit formula of a geometric sequence, we need the first term and the common ratio. So let's look at the sequence to identify that common ratio. So we start with b, and then the next term is b squared c. Okay, so we can multiply by bc to get from b to b squared c. Remember, we add exponents when we multiply the same variable together. To go from b squared c to b cubed c squared, we can multiply by bc again, right? B squared times b, 2 plus 1, would be b cubed. C times c, 1 plus 1 is c squared. Continuing on, if we multiply by bc again, we would get b to the 4th c cubed. Multiply by bc again, we would get b to the 5th c to the 4th. This would be another good example to point out if you didn't recognize that at first, take ratios. So if I take b squared c divided by the term before it, which would be b. Well, properties of exponents, 2 minus 1 is 1, so bc. Now do it for the next two terms. So take b cubed c squared divide by b squared c. Again, properties of exponents here, 3 minus 2 is 1, so b. C squared over c, 2 minus 1 is 1, so bc. And we can verify that the common ratio is bc this way as well. So our common ratio is bc. The first term is b. Not sure what happened there. Let's fix that. First term is b. So the explicit formula, a sub n, is equal to the first term, which is b, times the common ratio, bc, to the n minus 1. A lot of letters in this explicit formula, but we can use this formula to find any term of this sequence in terms of b and c. So it is correct. Our last example, determine all possible values of x that make the sequence below geometric. So we have three terms in the sequence, x plus 14, x plus 2, 2x minus 3. And we need to figure out what value or values of x make this geometric. Well, what's the property of a geometric sequence? There's a common ratio. Well, we multiply one term by to get to the next, stays consistent throughout the sequence. Well, as we just did in the last example, where I looked at dividing two terms to figure out that common ratio, we can do that here. So the common ratio between these two terms, I would take x plus 2 and I would divide it by x plus 14. That would give me my common ratio here. And then between these two terms, to find that common ratio, I would take 2x minus 3 and I would divide it by the term that comes before it, which is x plus 2. That also is the common ratio. Well, if both of these are the common ratio and this sequence is geometric, then I know that these two common ratios have to be equal. So again, running through that quickly. Take x plus 2, divide it by the term before to figure out the common ratio between these two terms. Take 2x minus 3, divide it by the term before, find the common ratio for those two terms. If our sequence is geometric, that common ratio should be the same throughout the whole sequence. So those two things should be equal. Okay, now that we got this set up, now we solve. We'll start by cross multiplying. So we have x plus 2 times x plus 2 equals 2x minus 3 times x plus 14. So we have to simplify first. So on the left side, we have x squared plus 2x plus 4. On the right side, we have 2x squared plus 28x minus 3x minus 42. Combining our like terms, x squared plus 4x plus 4 equals 2x squared plus 25x minus 42. We have a quadratic, so we need it equal to 0. Going to move all the terms on the left over to the right. So 0 equals x squared plus 21x minus 46. To make that look a little nicer, let's just switch the 0 around. So x squared plus 21x minus 46 equals 0. So we factor. So we need a factor pair of negative 46 that adds to 21. So that would be positive 23 and negative 2. So x equals negative 23, or x equals 2. Those are the two possible x values that would make this sequence geometric. Let's check and verify that. So negative 23. So if we plug negative 23 in, negative 23 plus 14 would be negative 9. Negative 23 plus 2 would be negative 21. And then 2 times negative 23 is negative 46, minus 3 is negative 49. So let's see, the common ratio there would be 7/3. So negative 9 times 7/3 would be negative 21. Negative 21 times 7/3 would be negative 49. So that works. And then the other sequence, x was what, 2? X was 2. So that would be 16, 4, and 1. That one's a little bit more obvious. 16 times 1/4 is 4. 4 times 1/4 is 1. But those two values of x make this sequence geometric. This is definitely a little more challenging of a problem, but I want us to focus on the idea of the common ratio and how we can find it by taking the ratio of any two consecutive terms in a geometric sequence. So whether our sequence has variables or numbers, we can always take the ratio of two consecutive terms to find the common ratio. Take a term, divide it by the term that comes before it. That's the technique. So in this video, we did a lot of work with the explicit formula for a geometric sequence, both creating it, given a whole bunch of different information, or using it to find a later term in the sequence. So it's really important that you practice with each type of problem so that you feel comfortable and confident coming up with the correct answer. Click the Amazon link down below for my algebra workbook so you can practice on your own. Give the video a like, and before you go, click that subscribe button so you can see more videos just like this. Thanks for watching.